A differential equation of this form is said to be exact if and only if partial m with respect to y is equal to partial n with respect to x. So what if they are not equal? And that's exactly what I want to emphasize here. Actually, what I really want my audience to take with them from this video is the idea of what is called an integrating factor. And it's a single variable function that you can multiply a differential equation by to make it exact. So let's suppose you had a differential equation bearing this form, which is known as differential form, and let's suppose that partial m with respect to y does not equal partial n with respect to x. In that case, you can't solve it like an exact differential equation because it's not an exact differential equation. But let's say that I had some function, I'll call it mu of x. Mu of x is what I'm going to define to be my integrating factor. And assuming that I multiplied my entire differential equation by mu of x, I would end up with mu of x times m of x y dx plus mu of x times n of x y dy equals 0. And assuming that this, what I call my integrating factor, mu of x, does what I said it would do, then it would make this differential equation right here, which I'll circle in red, it would make this here differential equation exact. So this here differential equation that I have written right here, let's switch gears for a second and forget about this m of xy or n of xy, because really the only thing that we're worried about is the function that's being multiplied by our differentials, by our dx and by our differential dy, and that the partial derivative of these functions with respect of the other variables are equal to each other. And then the differential equation is said to be exact if and only if that condition is satisfied. So what does that mean then? What does it mean if the partial derivative of this that I have here boxed in red, the partial of this with respect to y equals the partial of this right here with respect to x? Let's look into that. So this here differential equation is said to be exact if partial with respect to y of mu of x times m of xy equals partial with respect to x of mu of x times n of x y. And for the life of me, I don't know what's going on with my touchscreen that my handwriting is just suddenly getting so sloppy. But I'm gonna break down these partial derivatives here. So this right here, if I evaluate these derivatives with the product rule, note all the steps taken in producing this result. First of all, on my left hand side here I have the partial with respect to y of mu of x times m of xy, and that would be the partial with respect to y of mu of x times m of xy plus the partial with respect to y of m of xy times mu of x. And I simplified that. I'm going to circle that right here in red. I said partial m with respect to y. Now the partial with respect to y of mu of x is 0, so this goes away instantly. And on the left hand side here I have the partial with respect to x of mu of x times n of xy. And I left this alone for the time being simply to save space because I don't have much of it. So moving on with what I have on the left hand side of my equal sign, I have partial m with respect to y times mu of x, because those are the only two terms that survive, equal to what my right hand side of the equal sign evaluates to. Now if I take the partial derivative with respect to x of mu of x times n of xy, I'm going to take the partial derivative with respect to x of mu of x times n of xy. Remember, the derivative of the first term times the second term, so I'll circle that here in red. And note that the partial with respect to x of mu of x, since mu of x was a single variable function, I can write d mu dx. I don't need to worry about making it a partial derivative. I'm just differentiating with respect to x. No terms of y to worry about there. And now I have the second term times the first term times the derivative of the second term, because that's how the product rule works. So I have mu of x times the partial with respect to x of n of x. And I realize right here I have partial n with respect to y. Let me fix that. Hopefully nobody gets the wrong idea. It's partial n with respect to x. Actually, let me get my eraser here and repair that real quick. So hopefully nobody got the wrong idea there, but that's partial n with respect to x. That looks a little bit better. Not really. Well, anyhow, my objective here is to solve for mu of x, which is the function that I have defined to be my integrating factor. And if you notice, I've made a first order differential equation right here that would solve for mu of x. So it's interesting because we're solving a differential equation to help us solve a differential equation. It's like, bro, I heard you like differential equations, so this right here is a first order separable differential equation, and don't worry about the partial derivatives here. We'll treat this like an ODE. And hopefully you all are familiar with factoring and separation of variables, such that I don't need to go too deeply into detail with everything. But after subtracting my partial n with respect to x times mu of x, factoring out the mu of x, and then dividing my n of xy, this is what I end up with d mu dx being equal to. So here I've got what I left off with. D mu dx equals 1 over n of xy times partial m with respect to y minus partial n with respect to x times mu, or mu of x. And I'm going to quickly multiply out my dx and divide this mu. So I end up with d mu over mu equals 1 over n of xy times all of this crazy stuff. Partial m with respect to y minus partial n with respect to x. And after integrating both sides, I'm not going to be able to, well, I'm going to leave this in a generic form that will work for a formula. I end up with ln mu equals this integral right here. This crazy integral that's getting to be a real pain in the ass to have to keep writing. Times dx. And on the next slide, I'm gonna I'll exponentiate both sides here. So mu of x, lucky I have the space, equals e to the power of this integral. It's n of x, or 1 over n of xy times partial m with respect to y minus partial n with respect to x times dx. Hopefully this isn't too sloppy for it to be legible, but I'll box it in right here. So So here we have it, that the integrating factor mu of x is equal to this weird formula right here, and this has to be a single variable function of x. So I encourage you to try to do all of this to produce a single variable function of y, to produce an alternative formula for an integrating factor, mu of y. And giving you an idea of what that would consist of, it'd be the same exact procedure, except you'd be you except you'd be differentiating with respect to y instead.